So the goal of this tutorial is to show how we can plot the current versus voltage characteristics of a MOSFET starting from LTspice. This can be relatively useful, first for understanding the behavior of electronic components, such as, for instance, field effect transistors, but also, second, to understand how the parameters of the transistors vary as a function of the gate and of the drain bias. This can also be useful whenever you're studying electronic components to be used in specific circuits. In order to do so, we're going to draw a very simple circuit, where basically only a simple MOSFET and two voltage sources are present. In order to add our MOSFET to the circuit, I will of course click here, and then I will look for the NMOS button right here. I can place down my N-type MOSFET. You see the symbol of the MOSFET with the arrow which is pointing to the channel. And of course this is a generic MOSFET, but we would like to choose a specific one. I have made the choice for you, so you can right click here and click here, pick a new MOSFET. Of course there are several transistors that you can choose. I have chosen to use today this IRFP240 by International Rectifier. This is an N-channel MOSFET with a maximum VDS of 200 volt and a certain characteristics in terms of on resistance and gate charge. Of course, the choice is arbitrary, so you could have chosen any possible other MOSFET from the list, but I strongly encourage you to give a look to the datasheet in order to understand what the properties of this transistor are. Let's have a look to the datasheet. This is how the datasheet appears. You can see that this is effectively a transistor having a VDS of 200 volt maximum and RDS on, which is the on resistance of the transistor measured with a VGS of 10 volt, so gate source voltage of 10 volt, of 0.18 ohm. Now you can see here the symbol, and if I scroll down on this datasheet, I can find all the properties of the device that we're looking at. For instance, you can see the kind of package that we have. You see a drawing of the package and the absolute maximum ratings. Of course, we are doing simulations, but it's important for us to know what are the absolute maximum parameters that we should not try to exceed whenever we are using the transistor. For instance, we see the maximum limit in terms of VDS, drain source voltage is 200 volt, of gate source voltage is 20, and in terms of continuous drain current, it's around 20 amps. While on the other hand, if the current is then pulsed, the transistor can survive even with the maximum current, absolute maximum of 80 amps. These are kind of important parameters whenever you need to design a circuit. Now, in our specific case, we will be running simulations, but we will try our best not to exceed these values. So you will see for my simulations, I will try to stop with the VDS at values around 10 volt, so we make sure we are conservative, and also with the gate source voltage at values which are around 10 volt. Obviously, in a real-life circuit, of course, you would need to take into account about safe operating conditions in a much more serious way. Here you can find the specification of the transistors, and as you can see, apart from the drain source breakdown voltage, which I have already mentioned is around 200 volt minimum, what is important for defining a transistor is the gate source threshold voltage, which, as you can see, is in between 2 and 4 volt. Let's see how the model is developed. Then, of course, the datasheet gives us some specifications also on the gate source leakage. You know that typically the MOSFET is an isolated gate device, meaning that no current should be flowing through the gate electrode. Obviously, no oxide is ideal, and some current can flow through the gate electrode. Here, we are told that the maximum gate leakage that we can expect is around 100 nanoamps, but of course that's just a worst case scenario. We will see how this is modeled. And then of course we have other parameters which regard also the dynamic properties of the transistors, including the parameters which are called gate source charge, gate drain charge, which define exactly the switching properties of the devices. Of course, if you scroll down then on the datasheet, you might even find the typical characteristics of the devices. which are, for instance, the drain current versus drain voltage characteristics, or the drain current versus gate voltage characteristics, which are called respectively the output characteristics on the left and the transfer characteristics on the right. These are exactly the curves that we're planning to simulate by LTspice. Going back to LTspice, now it's time to draw our basic schematic. So we have chosen our transistor IRF P240. I can press OK, and now I see that the transistor name is appearing. Of course, we all remember that the terminals of the transistors are defined as gate, drain, and source. So what we need in order for the circuit to be simulated is to basically put in a couple of voltage sources. Let me add the two voltage sources that we're going to need, one for the drain and one for the gate. And of course, I need to connect some terminals to ground. Of course, I will connect to ground my source, but also the two negative terminals of the voltage sources that we are going to connect to ground with a wire in this way. Then, of course, I would like to give a name to these voltage sources. For instance, this voltage source, I may want to call it VD, and I use that for the drain. And the second one, I will call it VG, and I will use that for the gate. Of course, what I can do is also to place a label net, which can help me bring in the voltage to the drain of the transistor, and then to the gate of the transistor by using the tool label net as we have already defined it. Now, of course, these voltage sources might be set to a given voltage. For instance, I might want to fix a certain voltage, say 1 volt to the gate, 1 volt to the drain, and that would give me a fixed operating bias point. But of course, what I prefer doing today is to carry out a DC sweep, basically a double sweep, while I see the variation of the current, for instance, on the drain of the transistors, with varying both the gate and the drain potential. So let's try an example. The first thing I want to plot is what we call the IDVD, so drain current versus drain voltage characteristics as a function of gate voltage. This is also called the output curve of the MOSFET, and this is exactly what I'm going to do. In order to simulate this curve, I will press simulate and add a simulation command, and as you can easily imagine, what I need to do is to do a DC sweep, where I sweep two sources, the first one and the second one. For instance, let me start, and the first sweep I'm going to make is a sweep on the VD. So the name of the first source to sweep is VD, and I want to sweep it linearly from a start value of 0 to a stop value of 10 volt with an increment of, let's say, 50 millivolt. In this way, I will be sweeping the drain potential from 0 to 10, which we have seen is perfectly safe since the breakdown of the transistor, according to the datasheet, is 200 volt, with steps of 50 millivolt, which should give me enough resolution. Of course, this is going to plot me a single IDVD plot, but typically a transistor is a device where the drain current is modulated by the gate voltage. So I also want to modulate a second voltage source. So this is why I click here on second source. And here I want to modulate and to change, to sweep the value of the gate voltage. Once again, we know that the maximum voltage that we can apply to the gate is 20 volt. So to make things relatively safe, I will sweep the gate voltage only up to 10 volt. So I will choose a start value of 0, a stop value of 10 volt, and an increment in this case of half a volt, in order to have sufficiently large spacing between the curves. In this way, I am sweeping both the VD from 0 to 10 with a certain step and the VG from 0 to 10 with a certain step. I will attach this directive to my schematic, and then I will be ready for simulating. I will now launch the simulation, and as usual, a second panel comes out. Now, here, of course, I see my devices, and the first thing I want to do is to try to see if I am sweeping in the right way. the drain and the source, the drain and the gate voltages. Let me put a probe here. I see the voltage on the gate is sweeping from 0 to 10 voltage on the drain. And then, if I remove the VDD trace, I can add the VG trace, and I see that the gate voltage is swept from 0 to 10 volt, and I see that in a constant way as a function of VDS. So here, how to read this plot, on the horizontal axis, you have the first variable, which is swept, VD, and on the vertical axis, you have the value of the second variable, which is swept, which is VG, step of half a volt from 0 to 10 volt. Now that we know that we are applying the proper voltages, what we are interested in is in looking at the drain current. Let me press here. You see the current probe is appearing. And what I plot here, and I will enlarge it, is the drain current as a function of the drain voltage for different gate voltages. As you can clearly see, the characteristics of the transistors are typically, this is a MOSFET, have typically two different regimes. The first one is the linear regime, where basically the transistor is showing a ohmic behavior. You see a linear dependence of drain current on drain voltage. And then we have a second regime, which is called the saturation regime, where basically the current is reaching a fixed value, which depends mostly on the bias point that has been defined. In this way, you can see, we can also understand that with increasing gate voltages, of course, the transistor starts from a condition when it is off and gradually turns on until reaching a relatively large current. As I have shown you earlier, in DC conditions, it would be safe to use these transistors only up to 20 amps of current, which is the absolute maximum rating for the DC current of a transistor like this. In pulsed condition, the transistor can reach much higher current levels. And basically, this is what we can somehow imagine to simulate by means of a simulation like this. Keep in mind that, of course, if you're planning to use a transistor like this in DC condition, you would need to avoid going above 20 amps. This is the first thing I wanted to show. The second thing we can show is how to simulate not just the IDVD characteristics that we just saw, but the IDVG curves. In order to do that, the only thing we need to do is to change the sweep that we are using. And instead of sweeping as a first variable the drain and then as a second variable the gate voltage, we swap them. So we will set as a first source the gate voltage, and we will be sweeping the gate voltage, yeah, it's okay, with a step of 50 millivolt. And then we will step as a second source the drain voltage, VD, still between 0 and 10, with an increment, in this case, of 0.5 volt. In this case, we will start having, as a function of the gate voltage, the drain current for different values of the drain voltage. I will press OK, and then I am ready to launch my simulation. I launch my simulation. As earlier, I could test the values of the two parameters. Now the first parameter, which is swept, is VG. And as we can see, the VG is sweeping from 0 to 10 volt. Now, if I can cancel, delete this trace, and see what is doing the VDD. For different values of VG, the VDD is having all of these values, every half a volt, from 0 to 10 volt, which is exactly what I'm planning to do. So I have basically swapped the variation of the two voltages on the gate and on the drain with respect to the previous case. So now I can have a look to the drain current. I click here with the current probe, and as you can see here, I have now obtained, as a function of gate voltage, the drain current. If you remember, the datasheet was telling me that the threshold current was around 2 to 4 volt, which is exactly what I have found with my simulations. You see that, in principle, with increasing gate voltage, the channel turns on, and then, depending on the drain voltage, the current will be higher and higher. The same IDVG plot can be plotted also in logarithmic scale. So if I press here, I right-click, I choose logarithmic, I can see now the very same plot in logarithmic scale. So Here you can see more clearly where the threshold is. In fact, you can clearly notice that the threshold is in between 2 and 4 volt, approximately 3 volt. Below the threshold, the gate leakage is very low, is a fraction of nanoamp. And on the other hand, with increasing voltage, the current dramatically increases by several orders of magnitudes from the off condition to the on condition. And then, of course, the value of current in the on condition will depend on the value of drain voltage that we have used. This is basically a tutorial which is supposed to be telling you how to extract a device parameters starting from a simple LTspice simulation.